5 volts at 30 to 50 amps on the neutral line can indeed induce a voltage on the phase lines through electromagnetic induction. This occurs because the neutral line carries unbalanced current from the phases, creating a magnetic field. This magnetic field, in turn, induces a voltage in the nearby phase lines. This explains why you're observing a non-zero voltage reading on the phases even when they are isolated from the main power source. This induced voltage can lead to several issues within the electrical system. Firstly, false readings can occur. Voltmeters connected to the phase lines may indicate a voltage even when the phases are not actually energized. Secondly, sensitive electronic equipment can malfunction or sustain damage due to this induced voltage. Thirdly, safety hazards arise. The induced voltage presents a risk of electric shock or arcing if the phase lines are accidentally contacted. To address this voltage induction, it's crucial to ensure the neutral line is properly connected and grounded. Proper grounding minimizes current flow on the neutral line, consequently reducing the magnetic field responsible for inducing voltage on the phase lines. The magnitude of the induced voltage is influenced by factors like the distance between the phase lines and the neutral line, as well as the magnitude and frequency of the current flowing through the neutral line. Load fluctuations within the system can also cause the induced voltage to vary over time. When the induced voltage is significant, utilizing shielded cables or employing other methods to reduce electromagnetic interference becomes necessary. These measures help mitigate the impact of the magnetic field on the phase lines, preventing unwanted voltage induction. The following are potential problems that could arise in the electrical system. 1. False readings where voltmeters connected to the phase lines may indicate a voltage even when the phases are not energized. 2. Equipment damage where sensitive electronic equipment may malfunction or be damaged due to the induced voltage. 3. Safety hazards where the induced voltage can create a risk of electric shock or arcing if the phase lines are accidentally energized. To address this issue, it is important to ensure that the neutral line is properly connected and grounded. This will minimize the current flow on the neutral line and reduce the magnetic field that induces voltage on the phase lines. The magnitude of the induced voltage depends on the distance between the phase lines and the neutral line, as well as the magnitude and frequency of the current on the neutral line. The induced voltage can vary over time depending on the load fluctuations in the system. If the induced voltage is significant, it may be necessary to use shielded cables or other techniques to reduce the electromagnetic interference. When dealing with electrical systems, several factors can contribute to unexpected voltage readings and potential issues. Understanding these factors and implementing appropriate troubleshooting steps are crucial for ensuring safety and reliable operation. One such phenomenon is voltage induction, where a voltage appears on a conductor even when it is not directly connected to a power source. In this case, the presence of 5 volts on the phase lines when isolated from the breaker, despite the neutral being connected, suggests voltage induction. This can occur due to the magnetic field generated by current flowing through the neutral conductor. When current flows through a conductor, it creates a magnetic field around it. This magnetic field can induce a voltage in nearby conductors, especially if they are parallel and in close proximity. The magnitude of the induced voltage depends on several factors, including the current flowing in the source conductor, the distance between the conductors, and the length of the parallel run. Given the scenario, the 30 to 50 amps on the neutral line is sufficient to generate a magnetic field strong enough to induce 5 volts on the phase lines. This induced voltage can cause various problems in an electrical system. Firstly, it can lead to false readings on voltmeters. If a voltmeter is connected to a phase line with induced voltage, it will register a voltage even when the breaker is off and the phase line is supposed to be de-energized. This can be misleading and complicate troubleshooting efforts. Secondly, induced voltage can interfere with the operation of sensitive electronic equipment. Many electronic devices are designed to operate within a specific voltage range, and even a small induced voltage can disrupt their performance. In some cases, it can even damage the equipment. Thirdly, induced voltage can pose a safety hazard. Even though the voltage is relatively low at 5 volts, it can still cause a shock if a person comes into contact with the energized conductor. Furthermore, If the induced voltage is high enough, it can create arcing, which can ignite flammable materials and cause a fire. To mitigate voltage induction, several measures can be taken. One of the most effective methods is to properly ground the neutral conductor. Grounding provides a low impedance path for fault current to flow, which helps to reduce the magnitude of the magnetic field generated by the neutral conductor. Additionally, grounding helps to stabilize the voltage on the neutral conductor, which further reduces the induced voltage on the phase lines. Another approach is to use shielded cables. Shielded cables have a conductive layer that surrounds the conductors, which helps to block electromagnetic interference. The shield is typically grounded, which provides a path for induced currents to flow to ground, preventing them from causing voltage induction. In some cases, it may be necessary to increase the distance between the neutral conductor and the phase lines. The further apart the conductors are, the weaker the magnetic field that is induced. This can be achieved by using a different wiring configuration or by physically separating the conductors. Additionally, it is important to minimize the amount of unbalanced current flowing on the neutral conductor. Unbalanced current occurs when the loads on the different phases are not equal. This can be caused by a variety of factors, such as uneven distribution of appliances, single-phase loads, or faulty equipment. By balancing the loads and the phases, the amount of current flowing on the neutral conductor can be reduced, which in turn reduces the induced voltage. It's also worth noting that the frequency of the current flowing on the neutral conductor can affect the magnitude of the induced voltage. Higher frequencies tend to induce larger voltages. Therefore, if possible, it may be beneficial to reduce the frequency of the current. In practice, this is often difficult to achieve, as the frequency is typically determined by the power supply. Additionally, harmonics can contribute to voltage induction. Harmonics are multiples of the fundamental frequency, and they can be generated by nonlinear loads such as electronic devices and fluorescent lighting. Harmonics can increase the magnitude of the magnetic field and lead to higher induced voltages. To mitigate harmonics, harmonic filters can be installed. Harmonic filters are designed to reduce the amplitude of harmonic currents, which helps to reduce voltage induction. When troubleshooting voltage induction problems, it is important to use a high impedance voltmeter. A low impedance voltmeter can load down the circuit and give inaccurate readings. A high impedance voltmeter will not load down the circuit and will provide a more accurate measurement of the induced voltage. It is also important to use a clamp meter to measure the current flowing on the neutral conductor. This will help to identify the source of the unbalanced current. Additionally, it is helpful to use a spectrum analyzer to measure the harmonic content of the current. This will help to identify if harmonics are contributing to the voltage induction problem. In conclusion, voltage induction can be a complex problem that can cause various issues in electrical systems. By understanding the principles of voltage induction and implementing appropriate mitigation measures, it is possible to reduce the magnitude of the induced voltage and ensure safe and reliable operation. Always consult with a qualified electrician when working on electrical systems. When you encounter a situation where you're observing voltage on phase lines even when they are disconnected from the main power source, and this occurs while the neutral line is still connected and carrying a significant current, it's crucial to consider the phenomenon of inductive coupling. Inductive coupling is a process where a changing magnetic field produced by one conductor induces a voltage in a nearby conductor. In your case, the neutral line carrying 30 to 50 amps generates a magnetic field that induces a voltage in the adjacent phase lines. Several factors influence the magnitude of this induced voltage. These factors include the amount of current flowing in the neutral line, the proximity and length of the parallel run between the neutral and phase conductors, and the frequency of the current. The closer and longer the parallel run, the greater the inductive coupling and induced voltage. Moreover, higher frequency currents lead to a stronger inductive effect. This induced voltage can manifest as a reading on a voltmeter connected to the isolated phase lines. However, it's essential to understand that this induced voltage is not the same as a voltage source that can deliver significant power. It's more akin to a phantom voltage, readily influenced by the impedance of the measuring device. Potential problems can arise from this induced voltage. Firstly, it can lead to inaccurate voltage readings. A standard voltmeter might display a non-zero voltage on the phase lines even when they are intended to be de-energized, potentially causing confusion during troubleshooting or maintenance. Secondly, sensitive electronic equipment connected to these phase lines could malfunction or be damaged by the unexpected voltage. Thirdly, although the induced voltage is typically low, it can still present a safety hazard under certain conditions. If a person were to come into contact with the energized phase line while also being grounded, even a small induced voltage could cause a mild electric shock. To address this inductive coupling issue, several mitigation strategies can be employed. One effective approach is to ensure proper grounding of the neutral conductor. Grounding provides a low impedance path for fault currents, which helps reduce the magnitude of the magnetic field produced by the neutral line. Another technique is to use shielded cables for the phase conductors. Shielded cables have a conductive layer surrounding the inner conductors, which effectively blocks electromagnetic interference and reduces inductive coupling. Proper cable routing can also minimize inductive coupling. Keeping the phase and neutral conductors as far apart as possible reduces the magnetic field interaction between them. Similarly, minimizing the length of any parallel run between the conductors can also lessen inductive coupling. In some cases, it may be necessary to install line filters or surge suppressors on the phase lines to mitigate the effects of induced voltage. These devices help to absorb or divert unwanted voltage fluctuations. Another factor to consider is load balancing. Uneven distribution of loads across the phases can lead to excessive current flow in the neutral conductor, exacerbating the inductive coupling issue. By balancing the loads as much as possible, you can reduce the current in the neutral and lessen the induced voltage in the phase lines. It's also important to be aware of harmonic currents, which are multiples of the fundamental frequency. Harmonic currents can increase the magnetic field strength and contribute to inductive coupling. Using harmonic filters can help reduce the level of harmonic currents in the system. When dealing with inductive coupling, it's essential to use appropriate measuring instruments. A high impedance voltmeter is recommended to accurately measure the induced voltage. A low impedance voltmeter can load down the circuit and provide inaccurate readings. A clamp meter can be used to measure the current flowing in a neutral conductor, which can help identify sources of unbalanced current or harmonic currents. It's also important to note that inductive coupling can vary depending on the load conditions in the system. The amount of current flowing in the neutral conductor will fluctuate as loads are turned on and off, which will affect the induced voltage in the phase lines. Therefore, it's important to monitor the induced voltage under different load conditions to fully understand the extent of the problem. If the induced voltage is consistently high or causing significant problems, it may be necessary to consult with a qualified electrical engineer to develop a more comprehensive mitigation plan. This may involve more advanced techniques such as active filtering or redesigning the electrical distribution system. When addressing induced voltage in electrical systems, understanding the underlying principles and employing appropriate mitigation techniques are essential. Regular inspections and maintenance can help identify and address potential inductive coupling issues before they cause problems. This involves checking grounding connections, cable routing, load balancing, and harmonic levels. By implementing a proactive approach to electrical system maintenance, you can ensure safe and reliable operation. Additionally, consider using appropriate safety precautions when working on electrical systems with induced voltage. Always de-energize circuits before performing any work, and use appropriate personal protective equipment such as insulated gloves and safety glasses. This will help protect you from electric shock and other hazards. In summary, the phenomenon of induced voltage on phase lines due to current flow in the neutral conductor is a common occurrence in electrical systems. By understanding the factors that influence inductive coupling and implementing appropriate mitigation techniques, you can minimize its effects and ensure safe and reliable operation.